can save the Earth from this particular comet without taking too much risk with a system that is, touching the border of feasibility.
Did you look at planetary flybys for your plane change?
No. Planetary flybys, in fact, we talked about those, but planetary flybys require a fly out to some object that will allow you to do the flyby. Otherwise, how would you do this?
Mercury or Venus flyby?
Yeah. No, we didn't look into those. We didn't look into those. I think one point regarding this particular system is that it is not a complex system to launch on a short notice, right? If you want to build a bigger system with some flyby capability, you'll have to build it. But this is something that can in fact be stowed in space in some sort of parking orbit and just launch from there towards this random asteroid.
JPL's been doing planetary flybys for 40 years.
Yeah.
Ordinary spacecraft.
So it might be a solution there too. In fact, I think your point is that what should be done next is an analysis of alternatives, right? Yeah. So let's look at this solution versus other solutions. And maybe there is a better solution. Or maybe there are solutions that are at a higher TRL level that can be implemented tomorrow versus something like this that can be implemented in 50 years, who knows, right? So that's a very valid point here where we need to do a study where we look at all of the approaches and see what can be done and what works. So thank you. Anyways,
I'm sorry, we might have missed it because of the slides blanking out from the Zoom. But is the point of the solar sail, is that a means of the propulsion to approach the comet, or is this a means to actually deflect the comet? Kind of missed that point.
Yeah, no, not to deflect the comet. We cannot deflect the comet. It is a huge object that arrives at the okay, yeah, I can go back to the other chart here that you may have not seen. Yeah, so no, the intent is not to deflect the comet. It is impossible to deflect the comet even a few months before impact. It is just too large to be deflected at a few months before impact with the Earth. So the intent is to explode a large nuclear device next to the comet and just blow it up. That's the only way.
So it's just the propulsion means to get there.
Yeah, it's a way to shape the orbit for better intercept conditions than 2 weeks before impact. We just were trying to get the nuclear device as far away from the Earth as we could for safety reasons.
Thank you.
Sure. So that was a demonstration where we can potentially handle a comet threat, even at less than 2 years before an impact, if we had a solar cell system developed and ready to go on a short notice. It's part of the preparedness for planetary defense that we are advocating. And let's see. Oh, okay. So now, our latest research. Any of you heard about a company that's called Spin Launch? Spin Launch is a company that proposes to build centrifuges, evacuate them from air, and spin up the payload at tremendous speeds and launch those to suborbital velocities. Essentially, they say that their goal is to eliminate the booster, the first stage, the use first stage, and launch a second stage with an engine that could be ignited and push it into low Earth orbit. So seeing is believing, obviously. The company does exist so far. They invited me to give a talk. I came and gave a talk. And I said, how can I use their system to deflect asteroids? So on the surface of the Earth, you have to use huge centrifuges that are evacuated from air to be able to spin those payloads to tremendous speeds and launch them through the system into low Earth orbit. But if you are on an asteroid, all you need is a basic spinner, no need to evacuate any air from it. And looking at the pictures from DART, he said, wait a minute, the surface of a lot of those asteroids is littered with pieces of rocks that we can simply collect and catapult away from the asteroid and slowly push the asteroid away from the Earth. So we actually did a little study here. And that is a study we presented at the Planetary Defense Conference just a couple of months ago, where we looked at placing a small spinner notionally like that. And we looked at the DART mission and saw the very last pictures that came from DART. It showed the surface area of this asteroid. This is a treasure ready to be picked and thrown away from the surface of the asteroid. So we did a calculation. We put generic numbers here, representative numbers into the calculations. And we have found that we can deflect objects like the Chelyabinsk or Tunguska in just a few weeks of continuous operation. Several times a day, in the right direction, we can deflect those asteroids to one Earth distance, miss distance, which is good enough for us, within a few weeks of operation. So the technology that would be needed to do that is identical with the technology that Joel is developing to find those asteroids, approach those asteroids, land on them, do some engineering operations on the asteroids, in some case to utilize their resources. But in that case, it's just to throw those pieces away from the asteroid and push them and save the Earth from one of those objects. So with the case of the smaller asteroids like Chelyabinsk or Tunguska, it amounted to just a few weeks of operation, which is very feasible and doable. There are engineering challenges, no doubt about it, many engineering questions, and this is low TRL. So no doubt about it that this is just a concept. But we were looking at an interesting case, which is, let's see if it's in here. Yeah, so we looked at asteroid Bennu. Bennu is the asteroid that OSIRIS-REx has visited to bring some samples back to the Earth, I think this September. Bennu is considered a potentially hazardous asteroid because it has a non-negligible likelihood of impacting with the Earth in the late 22nd century, not 150 years from now. So yeah, we will leave this problem to next generations of planetary defenders, but I was looking if we can use that system to deflect Bennu, which is a huge asteroid, several hundred meters in size. And we found that with not even an optimized operation, over 100 years, we can deflect it away from the Earth just enough to eliminate the risk. So we can deal with large asteroids if we have enough time to deal with that, or smaller asteroids within a few weeks of operation. So this is our latest research. It's a back of the envelope type of research where we just looked at the basic physics. We might do another study on that where we'll look at the system engineering, but there are definitely many engineering questions associated with that. So I think in the final section here, I would like to go and visit the JPL page that tells us what's going on around our planet essentially today. But let's explore what's going to happen into the future and what could have happened in the past, in the recent past. I know that Joel Marks mentioned earlier about I think it was the Lexus Comet that came very close to us some 250 years ago, I believe, if I remember correctly. What was it?
253.
253 years ago. So we were lucky because 253 years ago, a comet of that size, if it collided with our planet, it might have changed the course of history. But let's see, just from the information that is known to us today, where are we headed and how fortunate we have been today. So going back to the JPL webpage here that shows the status as of today, let's increase the number of objects that are visible here. And let's look at the distance, at a unit of distance to the moon. I think we saw that earlier. We saw that there are a few objects that are small ones that are coming to a very, very close distance with us. This is about half time the distance to the moon, but it's a small object, 4 to maybe 8 meters. An object of that size most likely will burn out in the atmosphere. Maybe it will create a very large bolide and some explosion, but most likely it won't cause anything of significance. And in highest likelihood, it will occur over the ocean or over some uninhabited region of the world. But all of that is done in the next 60 days. Let's look into the distance passed and focus on objects that pass very close to our planet and they are not trivially small. So this tool is wonderful. It allows you to filter out things that you don't like to see. So I'm going to go into objects that are passing by our planet at less than the 5 times distance to the moon. And I'm going to apply this data in the next 60 days. We have 5 of these. All of these are going to pass by our planet in the next couple of months. But how about looking into the past? So let's look into the past. And this will allow us to go, well, let's do all available data. So I'm going to let the engine crunch on this. It will take a few seconds to update the page. All of this is done on the JPL side with their tool. So it's going to tell us about those objects. Good. Okay, so far we have thousands of these filtered along the available data of near-Earth objects. Let's narrow it down. So let's look at those that are not trivially small. So I'm going to take out those really, really tiny ones that we don't care about. Let's see how many of these will be left. So we are left with, see how many are left here. Number crunching, okay, 2,000. 2,000 over all times. Let's narrow it down even further and go to those that were very, very close to us, less than 1 time distance to the moon. Let's see what happens there. How many are going to be left?
So Lexel was 5 kilometer at 0.6 lunar distance, you said.
5 kilometers. So 5 kilometers is global, is almost at extinction level, almost, according to our understanding from Chicxulub, from the dinosaurs. It was 10 kilometers. So 5 kilometers in the same class of 10 kilometers. And it could have arrived at faster speed, which is more energy. It could be been heavier. So it's definitely in the class of global event. All right, how many were left? 119. Okay. In fact, let's narrow it down even in terms of size. Let's eliminate even those that are not. So let's see how many we are left with, those really big ones. And this is all time. So let's see how many are left that are, okay, so we have 40 of these. This is a good number to look at. Here's an object which is in the 700 meters that passed 2/3 distance to the moon in 1914. It's not 5 kilometers, but even half a kilometer object can destroy half of a continent.
I think it started World War I.
Yeah, could be. Here's about a kilometer size. I'm sorry?
Superman took care of that one.
Oh, it was, what's the name of that guy from the movie?
Clark Kent or
From Armageddon.
oh, Bruce Willis.
Bruce Willis must have been there. So here's a kilometer size at 90% distance to the moon, hundreds of meters. So I think we were really fortunate.
There's an important point that has to be made here.
Yes,
Because we know where the vast majority of the large asteroids
today,
are today.
Yeah.
But we only know where a tiny fraction of small ones are.
absolutely.
So there are thousands of them all the time.
How about hundreds of thousands?
Well, literally hundreds of millions.
Oh, yeah, yeah. But
But I'm talking about passing close to the Earth.
Yeah, near of object, I think, is estimated at hundreds of thousands. There are millions in the orbit, in the asteroid belt and so on and so forth, but those that have orbits that come close to the
Depends
Earth,
on your size cutoff. When they say hundreds of thousands, that's a pretty big cut.
around 15 to 20 meters and higher. So 17 meters is Chelyabinsk. I'll tell a short story about Chelyabinsk. Right? Chelyabinsk, if you saw the contrail that asteroid generated, it was very, very flat, about 20%, 20 degrees entry angle, which is not typical really. Most asteroids will impact the Earth at much steeper angle. So one of our colleagues from, thank you, Bill. Thank you, Bill.
Take care.
Take care. I will see you soon. One of the scientists from, I think it was Los Alamos or I forget now, one of those labs, he ran a simulation in which he replicated the Chelyabinsk object and showed where the majority of the energy would have been disposed at about 20 to 30 kilometers of altitude. And then what would happen if the exact same object had entered at 60 degrees, which is more typical? The energy would have been released at about 10 kilometers of altitude and would cause a much stronger shock wave and heat wave, probably would cause mass casualties over that city, will knock down a lot more buildings. So it means that even smaller objects in the class of 15 to 20 meters, which are within our lifetime, they're estimated to occur twice a century, which is something that could occur in your lifetime once or twice, maybe. Even a lot of us here, it could happen in our lifetimes. So we were looking at another study that looked at the technology that is used to intercept ballistic missiles. Can they intercept asteroids? And we showed that this can intercept incoming asteroids quite successfully. We ran hydrocodes to show that those asteroids can be disrupted at minutes before impact. So there is a lot of range of solutions that can be done that we are now only planting the seeds of what might be done in the future by future scientists and engineers along defending our planet. So this is, in my mind, an example of what could have happened that would have changed the course of history had any of these objects collided with us. These are objects between dozens to hundreds of meters in size. All have passed with less than the distance to the moon over the last century or so. We are just lucky that none of this impacted us. But if we go further into the future, I think where are we now here? 2001. No, I didn't want to do that. How do I get rid of this? No. So we are now in 2020. Okay, so we are somewhere in between here. 2028, there's going to be an object which is about a kilometer, zipping by our planet at about 2/3 of the distance to the moon. And it was discovered in 2001. So 2001 until 2028, it's 27 years. That's plenty. Joel, thank you very much. Are you leaving us?
Yes, thank you so much.
Thank you very much for your fascinating talk, and we'll be in touch.
Cheers.
It's an object of a kilometer size, which had it been discovered to be with a probability of impact with the Earth in 2028, 27 years is probably enough time to methodically build the systems that would destroy it or deflect it. Deflecting a 1 kilometer object is probably difficult even 20 years out, but maybe it would have been possible with continuous pushes. So maybe that's a study to be done. But it won't impact with us because it was determined that this object is going to pass at 2/3 the distance to the moon. However, in 2029, you have a question? Did you have a question?
No.
No. In 2029 is the infamous Apophis asteroid, which will pass at closer distance than the geosynchronous satellites, below the geosynchronous satellites. So that's going to be an opportunity to study that object. There are several missions that are being proposed to approach it and study it, and telescopes will be aimed at it. So we've never had such a significant size asteroid zipping by a planet that close. And this is really grazing the Earth, essentially. Go ahead. Yeah, Chris.
Quick question. You know, we talk about techniques to deflect asteroids, but you could, hypothetically, you could deflect it after it passes Earth, just to test the technology, to see what happens. So when you have no risk of the debris coming to hit the Earth, you know?
Well, maybe there is a possibility of deflecting the asteroids even after the close approach in the wrong way, so making them come back to us. There is something that's called keyholes,
Yeah,
and those keyholes are such regions in space in which if the asteroid had passed through this keyhole, it will come back to impact us in the future.
Yeah.
So we need to be very careful. Yeah, I mean, definitely do no harm is the principle here, but it requires some analysis to make sure that you didn't create a hazard out of another hazard, right? So yeah, the general principle is do no harm. And that's why the DART object was selected, because we knew that the DART asteroid will never impact with the Earth. And so that this is why it was selected for the demonstration mission. So yeah, you had a question?
Yeah, assuming you could mitigate that keyhole risk, do you think it would be valuable to do some technology maturation mission just to go through the process, get the industry involved and work on to what extent, just going through the process once, it's like dry run, right? So, or dress rehearsal, but in real case, and then you learn from the process of going through it one time. But obviously you'd have to mitigate that keyhole risk.
Yeah, my answer is absolutely yes. The advantage of Apophis is that it's at the same altitude as the geosynchronous satellites, which is a routine region for launch of spacecraft. So we are very much tuned to launch anything that we want to that region with not much preparation, really. It's just a matter of decision and money. Like Phil said, if somebody will give us a few $100 million, we can do it tomorrow. Right? The technology is ready to do that. It's just down to somebody deciding it's valuable to do.
I think
Today,
by 6 years from now,
Mhm.
you know, when it comes by in 6 years from now, if somebody gives you the money next year, then you could set up a technology demonstration mission to check it out.
Correct. Yeah, so it will have to occur in the next year or two. Somebody will have to say, that's a valuable mission to mature our technologies, to maybe achieve some other advantages and things like that. Currently, the majority of the goals associated with Apophis are scientific. So it falls on NASA's shoulders. And NASA is stretched with all kinds of other projects, not necessarily Apophis.
Is there a dual use potential with any valuable minerals on Apophis?
Minerals, I don't know. Potentially, maybe. We don't know. It seems to be just a regular regolith asteroid.
Like blast it with a laser and do spectrometry and kind of figure out what it's.
Yeah. So to characterize the object, certainly a characterization. So one of the things that could be very, very useful is to practice the characterization capability, right? In this case, it's a known asteroid. We can design the mission to approach the particular asteroid and do, train the sensors and how many systems do we have to get good coverage and things like that. So that we have the capability to approach a random asteroid, right? In the future, a real case will not have that type of situation where 20 years out, we know exactly the circumstance of this scenario. In the real world, somebody is going to tell you, hey, there is an asteroid that is coming our way in a year. Can you tell us how big it is from a dot of light in the sky? We need to have some system that can be launched very rapidly and tell us this is 100 meters, 200 meters, 500 meters. It's that heavy, it is pile of rubble or it is iron. so that at least we know the magnitude of the
Ideally,
threat.
get a delta V so you can measure its density, so you know it's a.
Exactly. Well, its mass. Really, what we are interested is to know its mass. The density times the volume is the mass, and what takes to deflect it is really the mass. So these kind of parameters are the parameters that would require very rapid characterization, which that type of mission to Apophis could start to develop. Right? If we develop a simple system that's hopefully affordable to launch something like a CubeSat or similar small sat type of system that can very quickly take a few pictures, use a sensor perhaps to tell us our densities, maybe take pictures from a few directions. This kind of stuff is something that would definitely advance our capability to characterize a random object that might approach us in the future. And among the community of planetary defenders, it's just a question of when. We are living in a shooting gallery, and it's just a question of hoping that nothing will impact us before we discover the majority of them and develop the capability to address them. But today we are not there. It's going to be decades until we are hopefully in a way that we say we discover the majority of the small and larger objects, and we have some capability to address a random scenario.
Yeah, the point has been made about the feasibility of a standby or perhaps even a rapid response type system for launch. And I know you mentioned the spin launch concept, and there was a concept that was proposed, and I believe even a company was founded, Quick Launch, by Dr. John Hunter, regarding the possible use of high efficiency gas cannon for space launching vehicles. And that should be that would be a fantastic concept for a very rapid sort of launch capability. I was just wondering if that has been looked at or explored in terms perhaps of planetary defense or exploratory type of launches for near Earth approaching asteroids.
Not by us. I think other groups have looked into what is called the mass driver concept, in which you just throw pieces of the asteroid away off the asteroid by railgun or by whatever other methods. We just looked at the spinner as a method of doing this with a simple electric device. I think that the best thing to do, like I mentioned earlier, is to do a analysis of alternative type of study in which we look at all of the proposed methods in a systematic way, and it's just decide and understand in a systematic system engineering way which of these methods have any advantage over others in terms of cost, feasibility, reliability. So I think it's a good, valid question. We did not do a comprehensive. If somebody would give us the budget to do that, we would be happy to do that. But those budgets are very hard to come by.
I see.
Yeah.
This is actually the concept here is actually from Earth's surface, and it would be the use of a cannon that actually almost in the Jules Verne's version of a trip to the moon that would actually be capable of launching vehicles. This is a high efficiency type cannon that uses a gas combined with hydrogen and helium sort of chambers that propulse that would be the propulsion for a projectile that would reach space. And the concept has been, I think, proposed, and even some preliminary type work has been done with this for these type of launch systems. But I was just wondering if perhaps maybe that had been looked at as an alternative. Then that would not require a rocket built or anything. It would just be a projectile that would be necessary for the launch. So it could provide perhaps a very quick response or turnaround time for a launch type system. So I was just curious if that had been one of the things that you might have looked at.
Yeah, no, we haven't looked into this particular method. I think it would be worth comparing to any other method that might be proposed. One of the challenges with any proposed method is that a realistic asteroid scenario would be a random object arriving from a random direction. So you would have to be ready to launch from, let's say, from the surface of the Earth to a completely random direction quite rapidly. And so that would be one of those criteria of dealing with short warning, right? If you have enough time, then all of this is your point, because you'll have enough time to design the system corresponding to this particular scenario parameters. But in a very short warning, when a random object appears from a random direction, how fast can you react is a critical question. But I think it's another good point in which we have to study those methods in a comparative study, which will tell us the advantages and disadvantages of each of these approaches. So I think this is a good point, but we have not done that study today.
Can I ask you,
Yeah.
your prior slide in the corner, it talked about, the prior slide had something about spin launch being deployed on the moon. Would be the next step. And yeah, it's down on the far right corner, I believe. Am I wrong? Spin launch, is this on-site centrifuge? There it is, down there. Almost the last, and then on the moon in the near term. And so the question was, is there any benefit to being able to launch from the moon if you were going to intercept? That is, you don't have atmospheric weather and things like that. And the delta V is very short, and something like the gas gun or a spin launch, or it's much more practical to actually get to intercept the body.
Definitely yes. Definitely yes. The moon is the same type of environment as the asteroid. You don't need to protect against the atmosphere there. You only need a spinner. You can place several spinners in different directions that could launch at random directions. So we looked into that. We didn't do any calculations, but we considered testing the system on the moon just to show that it's doable. The advantage of doing it from the moon is that there is a Swiss Lunar Space Initiative that's ongoing now. It could be part of the ongoing process of creating presence on the moon for different, objectives. And this could be part of it. The same system could be used for rapid transportation of payloads between one region of the moon to another region of the moon, right? You don't have a rail system on the moon currently, but maybe you can do a spin of an object from one region to another region, have it captured by some means, and use the same system to launch a characterization object towards an asteroid, for example.
Sure. I suspect that if you had some other conventional propulsion system on the moon too, like a way to get back to Earth easily, if you have some chemical propulsion system, you could also launch that at will without, in order to have a quick intercept. That's just my, from considering all the dynamics. That would be.
Oh yeah, it makes sense. At the moon, obviously, we are at the edge of the sphere influence of the Earth, so launching from there should be much easier than launch anything from
the delta V is small.
The delta V, no atmosphere, so that's something that definitely is more feasible. But again, we are very low budget. We do something when we have a little bit of a shoestring budget to study this. I think NASA is doing a lot of those studies on their own. They have more of these resources. We just pick, those areas that weren't touched by others.
No, the question is more just, would it make sense to consider a planetary defense system that is based on the moon as in order for quick response?
Yeah. We looked into.
And dual use, and for use to send payloads elsewhere.
Yeah, we looked, for example, into the use of hypercones, those propellants that are self-igniting, placed or parked at orbits around the moon, right? So with a very little bit of a push and correct timing,
Right.
they can be, launched towards a random asteroid. But we haven't done any serious study on that. All of these are really good ideas that are lacking resources to seriously study those. One more. So I think we looked at this last page. We saw what's coming. We saw how fortunate we were in the last century, not being hit by fairly large objects that happened to miss us by not much in the last century. And in the near future, there's going to be opportunities to for objects to pass by us at distances that are not negligible. I'm just looking at those distances here. So we have in the year 2100, actually, right? This is after distance to the moon, objects that are in the hundreds of meters. So this will be left for the next generations to address.
These are the ones we know about.
These are the ones we know about, exactly, today. The table is going with the device that Amy is going to put out in a few years in L1, in Lagrange point L1. Hopefully in 10, 50 years, we are going to increase the amount of knowledge by an order of magnitude. And at least we know more about what can and cannot happen. But yeah, this is part of the reality in which we live. We live in a shooting gallery, basically. And we just need to hope that before we develop this capability, we are not hit by something that can change the situation. As an example, one of the studies that we've done with the lady that was here earlier is showing that even small objects can cause significant disruption. For example, if a small asteroid the size of Chelyabinsk or Tunguska, which are small objects and very frequent, relatively speaking, hit the California aqueduct and disrupt the water supply to Los Angeles, that's a major disruption to our city. What will Los Angeles do without half of its water? Major disruption, right? So even small asteroids, small impacts can cause significant damage if they hit in the wrong location. Water supplies and some other key installations or key resources that could be disrupted with small objects. Things like these are to be considered. So I think with that, we've wrapped up today. Are there any comments or questions online or from the audience at all about today's presentation? We went over, yes.
I have a quick question. Remember Dr. David Levy was talking about when he was asked how to evaluate the impact for the comet Jupiter or Earth, and he mentioned a parameter called delta.
Delta?
Remember, he said he was looking at the chart of the delta, and the smaller the delta, the higher probability of the impact. So honestly, initially I was thinking maybe there was a parameter here related to that.
No.
But we can chat about it later.
Not that I'm aware of.
Okay, no worries.
Not that I'm aware of. I think that JPL maintains an assessment of the risk of impact based on Monte Carlo studies that they do for every object. So they run a lot of scenarios depending on the accuracy of the discovery, and they estimate the likelihood of impact into the near and distant future. And I think they have, let's see, do I have it here? Okay, they add the closure post. So they may have changed their website a little bit, but they used to have like a minimum distance and nominal distance, which relates to the risk. So I'm not sure what the data is. That's a different thing. Maybe just a measure of the accuracy of the prediction of the impact likelihood of the comet. With that, I'm done. If there are no questions, I'd like to thank you very much for attending this long day. We have talked about from Amy, right? A new sensor that's going to be deployed to space. We heard about from Joel Marks about how to think about the risk, right? What sort of risk basis would you like to apply when you make decisions? And we heard about what's the third one? I forgot. Alisa, yeah, about the legal challenges. You know, any decision that would have to be made is have to be overcome the legal language, and it had to be done in a collaborative fashion with the nations of the Earth, right? And we have, of course, David Levy about the discovery, his, I would say, philosophical and artistic way of describing being part of that event. I mean, it's a lifetime experience that he's carried through the last 30 years, right? It's amazing. And we heard from Bill Ayler, who has been the founder of those international planetary defense conferences from 2004 until today. He continues to co-chair those conferences. I joined those almost from the first one, from the second one. And I'm hoping to continue to serve those community in the next few years. And what else did we hear? We heard from
Then is Dr. Serso, and then is Mark, and then it's Madhu,
Right.
Theo, and it's you.
Yeah, so mining those asteroids, reflecting them in the movie, and also shining laser into those. So with that, I would like to thank you very much.
Thank you, Ken.
Thank you.
The
The biggest thank to Dr. Nahum Melamed. He has been wonderful leading the community and the technology. Also, Lex, thanks. But this is our appreciation for him. And thank you so much, Dr. Melamed. This is wonderful. This is amazing. Then this is keep everybody aware and continue to advance the technology.
Thank you, Nahum. It's a pleasure to listen to all the speakers that I heard, and I hope all of us go watch Asteroid City Sunday.
Thank you, thank you.
Yeah, everything that has an asteroid in the name, I'm hooked.
Thank you, Ken. Thank you for a good
All
meeting.
the best to you, Madhu, and good to hear you. We'll see you soon.
Okay, thank you, everyone. So let's wrap up today. Thank you, everybody, for joining us. I think there's actually one thing I do want to mention. Yes, of course, for next year, we'll definitely plan to get Dr. Levy here, and we'll try to do is see if we can expand it for kind of real conference for maybe 2 days. The first day asteroid, second day, Comet, or just combine 1 day. And then the other thing, actually, we actually have been putting some more effort to outreach to local high schools. And I realized there's some very amazing high school doing very good project. And I learned that with outreach to a high school in Long Beach, they had a project doing the Mars settlement. And I actually tried to get the 3 teachers today to come here, but unfortunately they didn't come. But I'll keep trying to them. I think that would be a great idea that to, the primary defense project. And for example, Mark talking about this approaches, as a practice. And it could be a collaboration with the schools, and you can lead the project. So we'll keep trying to do this, connect to the local university and school, and we'll be exploring. There are several amazing high school and amazing projects. So that's something, a direction we can aim for. So the other issue I think is you mentioned about some university like Santa Barbara. They have the theory about this Tunguska.
Santa Barbara. It's about the laser. Santa Barbara is Phil Lubin. He does research on the laser deflection of asteroids. And I'm not sure what's the status of this research now. I talked with him a few years ago. He was still active. I'm not sure what he's doing now on the topic, but there is a bunch of research that was published on it that anybody who's interested, I think, did you ask? Yeah, I mean, it probably is going to be.
I've met him.
You met him, yeah, so.
I have included Lubin's website on my charts, Nahum. And,
Very good. We'll reach out to him next year again. But I was referring to a theory talking about Tunguska. I think when we chatted, you say you saw a paper and published about a theory like glancing through the atmosphere. And they have the theory to explain the impact Tunguska explosion.
I can't recall it at this point, so.
Okay, don't worry about it. We'll keep working on it. All right, thank you, everyone. So see you next time. And someone talked about the threat from radiation. On July 15th, we'll have a space environment and the solar activity event. So stay tuned. See you next time. Thank you. Have a wonderful weekend.
thank you, Ken. Bye.
Thank you, Madhu.
Thanks.
Thank you. Thank you. Wonderful.
So,
See you
see you next Friday.
That'll be fun.
Okay, thanks, Phil.
See ya.
All the best.
Thank you.
Well, Dr. Melamed,
Melamed, yes.
is there a question for you?
Yes.
Are most of your studies on like kind of budget solutions sort of thing. I always feel that